Take a look at worksheet number 16, questions 5, 6, and 8. Starting with number 5, it says light passes from air in a diamond at an angle of 15.0. What's the angle at which it leaves the air diamond boundary? Draw a picture here. This is our boundary. This is our normal line right here. Usually I say it's going from the top one to the bottom one, although it doesn't really matter. If that's the case, then we're going to say the top is air and the bottom is diamond. And if I look on that table that you were given, you see the index of refraction for air is 1.00. For diamond, it's 2.42. Now, the index of refraction of air is also given on your data sheet, but that's an easy one to remember as well. Diamond isn't given on your data sheet. If you ever need that one, it'll be somewhere probably buried in a page of information that you're going to have to locate. It'll be there. You don't have to memorize that number or any other indices of refraction, but you will have to be able to potentially find it buried in potentially a page of information. All right, we got this, this light going from air into diamond, like this, at an angle of 15 degrees. Now, sometimes the wording of a question isn't great. There was a couple questions on the sheet where that was the case. Sometimes it's just a little bit confusing which angle we're dealing with. Sometimes it's easier to look at what you're looking for. This one says the angle at which it leaves the boundary. If we're looking for where it leaves the boundary, then we're looking for theta 2, and we've got theta 1. Right? No matter what the wording of this was, okay, this must be theta 1. Now, if we're going from air into diamond, from low to high index of refraction, what's going to happen to this light? Is it going to speed up or slow down? As n goes up, v will go down, right? And if v goes down, theta will go down. So we would expect an angle down here, theta 2, that's smaller than theta 1. How much smaller? I'm not sure exactly. Actually, to be honest, I look at this and think it's probably going to be quite a bit smaller because the index of refraction is quite a bit different from air to diamond. In fact, you don't get a bigger range of index of refraction than you do for air and diamond. All right, so let's use Snell's law here. Snell's law says sine theta 1 over sine theta 2 equals v1 over v2, lambda 1 over lambda 2, or n2 over n1. They're inversely related, theta and lambda, or sorry, theta and n. And that's why when the index goes up, the angle goes down. Now, what are we looking for here? We've got theta 1, so we'll say sine 15 degrees over sine theta 2, which is what we're looking for right here, equals n2, which is 2.42. It's going to medium 2, and it's coming from medium 1. So a little bit of algebra here. The 1 goes up, the 2.42 goes down, the sine theta 2 goes up, and it ends up looking like this. Sine 15 degrees over 2.42 equals sine theta 2. And now what we're going to do is simply take the inverse sine of that. I say simply. It's not quite that simple when we've got a trigonometric expression inside another trigonometric expression, but it'll work. We're going to say the inverse sine of, let's use another bracket here, sine 15. Okay, so the inverse sine of sine 15 divided by 2.42. Now, there's a lot of brackets there, so let's just make sure that the brackets work out, okay? Brackets around the 15, brackets around the sine, brackets around the whole thing. Looks like it's good. 6.1 degrees. Anybody else get that? 6.1 something degrees. 6.14 degrees. So yeah, our angle was quite a bit different, right? It went from 15 to 6, and that happened. We got such a big difference in angle because we had such a big difference in index of refraction from medium 1 to medium 2. All right, who asked me for that one? Brandon, was that you? Yeah. Oh, the other one? Does that make sense? Yeah. All right. Number 6 says when light passes from water into quartz glass, it refracts at an angle of 25 degrees. What's the angle of incidence? Let's draw it out here. There's my normal line, always drawn at 90 degrees. This is my water, and this is my quartz glass. I remember the index refraction of water is 1.33. I don't remember the index refraction of quartz glass. I want to say 1.47. Yeah. I always remember that one of them is 1.47, one of them is 1.52, but I never remember which one is which. So I guessed right this time. All right, so it's going from water into quartz glass. It's going this way. It refracts at an angle of 25 degrees. Is it going to bend toward the normal line or away from the normal line here? In other words, is theta going to go up, down, or up? It's going to go down because the index went up. Theta is going to go down. Now we're given theta 2 in this case. It says it refracts at an angle of 25.0 degrees, and we're looking for the angle of incidence, theta 1. Now that's good. Theta 1 I think is a little bit easier to solve for because we don't have to get it to the top. It's not much of a difference, but sine theta 1 over sine 25 degrees equals N2, which is 1.47 over 1.33. So let's say 1.47 divided by 1.33. And now let's multiply that whole thing by sine 25. And now let's take the inverse sine of that. And we get 27.8 degrees. So theta went down from 27.8 to 25. Would we expect it to go down? N went up, theta went down. Why didn't theta go down by as much as it did in the last question? Because the n values are a lot closer together, good, than they were in the last one. Right? We went from 15 to 6 because we were going from 1 to 2.42. Here we went from 28 to 25 because we were only going from 1.33 to 1.47. Right? The bigger the difference, the more refraction you're going to get. All right, 5, 6, and what was the other one we need to go over? 8? 8 says determine the ratio of the speed of light in crown glass to the speed of light in quartz glass. Crown glass, I think, was 1.52, and quartz glass was 1.47. Is that right? Yeah. Or do I have them mixed up there? Nope. I'm going to call this NC, and I'm going to call this NQ, although it doesn't really matter. What I don't want to do is call it N1 and N2. It's not really wrong to do that, but I just don't want to get it mixed up with a Snell's law, like a regular Snell's law problem. We're not going from quartz glass to crown glass or vice versa. So I want to change the notation so that I don't think that I'm doing that. Now, if I want to find the ratio of the speed of light in these two materials, normally what I do is say VC over VQ, and I would solve it. But I got a problem. I don't know what VC or VQ is. You do have a couple of options. One is the long way, and the other is the short way. The long way involves going over here and saying, well, look, I know the index of refraction of crown glass, and I know the speed of light. I can solve for the speed in crown glass, do the same thing for quartz glass, and then divide them. Does that work? Absolutely, it does. But I know the ratio of the speeds is equal to the inverse of the ratio of the indices of refraction. So why don't I just do this? 1.47 divided by 1.52. Does that make sense? Okay, I know that N2 over N1 is exactly the same thing as V1 over V2. So if I want the value of V1 over V2, then why not just get the value of N2 over N1? Or in this case, NQ over NC. What does that work out to be, like 0.9 or something like that? 0.967. How many people did it this way? Okay, how many people did it this way where they solved for the value of V and then divided V's? Okay, did you get 0.967? Go figure, right? In the end, the N's effectively, the C's effectively end up canceling out, right? All right, so the ratio, we say 9.67, or 0.967. We'd say the ratio of crown glass to quartz glass would be 0.967 to 1 as a ratio here, right? Make sense? Good. What's another word for ratio? Divide. That's what we did, right? We divided. We divided V1 by V2, which was the same thing as saying N2 divided by N1. What's another thing besides ratio, divide? Third one? Compare, yeah. If we said compare the speed of light, then we do exactly the same thing.